In the last session, I have discussed about node, nodal plane, and shapes of S, P, and D atomic orbitals. After that, I have discussed about various tools for filling the atomic orbitals. That is, we have discussed about the Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity for filling up of the atomic orbitals. In today's session, I will be discussing about the stability of the atomic orbitals, that is stability of the half filled and completely filled orbitals. Then after that, we'll study about the relative energies of the atomic orbitals. So let us begin. First, we'll see the stability of completely filled and half-filled orbitals and the concept of exchange energy. The exactly half-filled and fully filled orbitals have greater stability than other configurations. The reason for the stability are symmetry and exchange energy. The electrons present in different orbitals of the same subshell can exchange their positions. That is, the half-filled and fully filled orbitals have greater stability when compared to other configurations. They will be having the higher stability when compared to other configurations, and the reason for the stability of these half-filled and completely filled orbitals are that symmetry and exchange energy. Symmetry and exchange energy are the two reasons for which the electrons, for which the half-filled and completely filled orbitals have greater energy and greater stability. The electrons present in the different orbitals of the same subshell can exchange their positions. The electronic configuration of most of the atoms follow the basic rules. That is, the electrons which are present in different orbitals of the same subshell. For example, the electrons in the p subshell, in the px, py, pz orbitals, they can exchange their energies, they can exchange their positions, and the electronic configuration of the atoms will be following certain basic rules. That is, in the last session we have discussed about the rules of Bohr principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. These are some of the basic rules which we are using for filling up of the electrons or for writing the electronic configuration of the atoms. But however, in certain elements such as copper or chromium, where the two subshells, that is 4s and 3d, differ slightly in their energies, an electron shift from a subshell of lower energy 4s to a subshell of higher energy, that is 3d, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. For example, certain elements such as copper or chromium, wherein the two subshells, that is 4s and 3d subshells, they are differing in their energies. They have slight difference in their energies, and the electron will be shifting from the subshell of lower energy, that is from 4s subshell, that is a 4s subshell has the lower energy. The electron will be shifting from subshell of lower energy, that is 4s subshell, to a subshell of higher energy, that is 3d subshell, in such a way that the shift of the electron should result the orbitals of the subshell, which should have higher energy. They should have higher energy, and they should become either completely filled or half filled subshells. We have to keep it in mind that when the electron shifts, or when we shift the electron from lower energy subshell to a higher energy subshell, The shift should result or it should give the orbitals of the subshell with higher energy, and the orbital should be either completely filled or half filled. Therefore, the valence electronic configuration of chromium and copper are 3d5 and 4s1 and 3d10 and 4s1 respectively, and not 3d4 4s2 and 3d9 4s2. That is, in general, if we write the electronic configuration without any rule, we'll be writing as argon 18 3d4 4s2 for chromium. But according to this, if I have to shift the electron from lower energy subshell, that is S subshell, these two electrons I cannot shift to the D subshell. Why? Because while shifting the electrons, we have to keep it in mind that the subshell should become either completely filled or half filled. If I shift two electrons to the D subshell, it it doesn't become either completely filled or half filled subshell. So I will be shifting one electron from this S subshell to the D subshell. So the D subshell will contain 5 electrons. Ultimately, there will be 5 electrons in the D subshell after shifting the electron from the S subshell. So it becomes a half-filled D subshell. It becomes a half-filled D subshell. We know that D subshell has 5 orbitals and it can accommodate 10 electrons. So we are shifting one electron from the S subshell to the D subshell. So totally there will be 5 electrons, each electron in each orbital. So it becomes a half filled D subshell. So it will be having greater stability. So similarly for this, so the electronic configuration becomes argon 18 3d5 4s1. In general, we will be writing 3d5 4s1. That is, outermost electronic configuration will be 3d5 4s1. So this becomes a half filled atomic orbital D subshell, half-filled D subshell, so the stability also increases. Similarly, for the copper, if we in general without the rule, if we write the electronic configuration, valence shell electronic configuration, it will be 3d9 4s2. It will be 3d9 4s2. But the D subshell will be having 9 electrons. It is neither the completely filled nor the half filled. So what we'll do, we'll be shifting the electrons from the S subshell, that is lower energy subshell, to the higher energy subshell, that is D subshell. We'll be shifting one electron from S subshell to the D subshell, so that there will be a 10 electrons in the D subshell. Totally, there becomes 10 electrons in the D subshell, so that it becomes completely filled subshell. It becomes a completely filled subshell, and the electronic configuration is 3d10 4s1. The electronic configuration will be 3d10 4s1, which means it is a completely filled orbital. So it has a greater stability. It has been found that there is extra stability associated with these electronic configuration. That is, the configurations, these configurations, that is 3d5 4s1 and 3d10 4s1, they are having extra stability. Why? Because they are completely filled and half filled atomic orbitals. So in that case, in such configuration, in such electronic configurations, they will be having or they will be associated with the extra stability. The completely filled and the half-filled subshells are stable due to the following reasons. Now we understood that the half-filled and completely filled orbitals are they are stable. They will be stable, but we have to study the reasons. The reasons for their stability is that first reason is the symmetrical distribution of the electron. The reason for the stability of the completely and half-filled atomic orbitals is that the first reason is the symmetrical distribution of the electrons. Second one is the exchange energy. Second reason is the exchange energy. It is well known. First, we'll see the symmetrical distribution of the electrons. It is well known that symmetry leads to the stability. The completely filled or half-filled subshells have symmetrical distribution of the electrons in them and are therefore more stable. We know that symmetry leads to the stability, and the completely filled as well as the half-filled subshells have symmetrical distribution of the electrons. The orbitals have a symmetrical distribution of the electrons, so therefore they are stable. Electrons in the same subshell, that is here we are talking about a 3D subshell, have equal energy but different spatial arrangement. The electrons which are present in the 3D subshell, all the electrons which are present in the 3D subshell will be having equal energy, but they will be different in their spatial distribution. Consequently, their shielding of one another is relatively small, and electrons are more strongly attracted by the nucleus. That is, shielding is nothing but it is a blocking of the electrons, valence electrons, towards reaching the nucleus. So here the shielding of one another is small. It is small, so the electrons are, they are strongly attracted towards the nucleus. The second reason is the exchange energy. The stability effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of the subshell. Here we observe the stabilizing effect when there are two or more electrons which are having same spin and are present in degenerate orbitals of a subshell. Degenerate is nothing but a Degenerate orbitals are nothing but orbitals having same energy. Here we observe the stabilizing effect between the two or more electrons with the same spin. If the two or more electrons are having same spin and they are present in the degenerate orbitals, orbitals with the same energy of the same subshell, these electrons tend to exchange their positions, and the energy released due to exchange is called as a exchange energy. These electrons will be exchanging their positions, and during their exchange there will be a release of energy due to that exchange. So that exchange is called as, that energy released during the exchange is called as a exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum, and so is the stability. Here, the number of exchanges will be maximum when the subshell is either completely filled or half filled. If the subshells are either completely filled or half filled, in that case we can observe maximum number of exchanges. We can observe maximum number of exchanges of the electron positions. So as a result of this, we can observe maximum exchange energy with maximum stability. So next concept is relative energies of the atomic orbitals. Relative energies of the atomic orbitals can be compared with the help of energy level diagrams. The diagrams for the hydrogen atom and multi-electron atoms are discussed. Here, for studying the relative energies of the atomic orbitals, we are taking the help of energy level diagrams. Using the energy level diagrams, or comparing between the energy level diagrams, we will be studying the relative energies of the various atomic orbitals. And for our discussion, we are using the energy level diagram of the hydrogen atom, that is single electron atom and multi-electron atom. That is, for studying of the relative energies of the atomic orbitals, we are using the energy level diagrams of a single electron atom and multi-electron atom. First one is the energy level diagram for the hydrogen atom. The energies of the different orbitals in the energy level diagram depend upon the principal quantum number n only and are independent of the azimuthal quantum number L. The energies of various orbitals in the energy level diagram will be depending upon only the principal quantum number. That is, in the energy level diagram, the energies of various orbitals will be depending upon only single quantum number. That is, it will be depending only on the principal quantum number n. It does not depend on the azimuthal quantum number L. This means that all the orbitals which belong to a particular shell have the same energy. It means that all the orbitals which are related to a same shell will be having same energy. See here the example, you will understand how they will be having the similar energy or same energy. For example, 2s and 2p orbitals having the principal quantum number n is equal to 2 have the same energy, and the same is also true for the orbitals belonging to the higher energy shells. That is, for example, if we are considering the 2s and 2p orbitals which are having the principal quantum number, that is, we know that n is equal to 2 for 2s and 2p orbital, they will be having same energy. And this is also similar for the higher energy cells. See the energy level diagram here. This is the increasing energy order of the orbitals. The first subshell we have is the 1s shell, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4f. In the case of single electron system or in the case of hydrogen atom, the two orbitals, that is, the two shells will be having similar energy. The two shells will be having same energy. For example, here in the 2s orbital and 2p orbital, or we can say 2s shell and 2p shell, both are having same energy, and the orbitals in the 2p shell will have the same energy. They will be having same energy. All the orbitals will be having same energy, and this is similar to all the higher energy orbitals. For 3s, 3p, and 3d orbitals, also they will be having similar energies. They will be having similar energy. For example, 1s orbital of 3s orbital and 3p orbitals of 3p or subshell and 5d orbitals of 3d subshell, all will be having same energy. They will be having same energy. And in the case of 4s, 4p, 4d, and 4f, all the orbitals, all these orbitals will be having same energies. The energy level diagram is also applicable to one electron species such as helium plus 1, lithium plus 2 ions in addition to the hydrogen atom. This energy level diagram is not only applicable for the hydrogen atom, it is also applicable for the one electron system, or we can say one electron species such as helium plus 1 and lithium plus 2 ions. Here, in the case of single electron species or single electron system, the two shells will be having same energy. The 2s and 2p orbitals have the same energy. These will be having same energies. And the orbitals of 3s, 3p, and 3d will be having same energy. And the orbitals of 4s, 4p, 4d, and 4f will be having same energies. And this energy level diagram can also be used for the single electron species like helium plus 1 and lithium plus 2 ions. Next we have is the energy level diagram for the multi-electron of atoms. The energy level diagram for atoms containing any number of electrons differ from the diagram for one electron atom, that is, the only the orbitals having the same value of L and not the same value of N have same energy. Here we know that the energy level diagram for the single electron species and multi-electron species will be differing from each other. That is, both the single electron system and the multi electron system will be having different energy level diagrams, and the only the orbitals which are having same value of L and different value of N have same energy. They will be having same energy. For example, for n is equal to 4, the orbitals belonging to 4s, 4p, 4d, 4f subshells have different energies, but those present in 4p subshell, that is 4px, 4py, 4pz, have the same energies. For example, if we consider principal quantum number, that is n is equal to 4, the orbitals which are belonging to the 4s, see the energy level diagram. This is the increasing order of energies of the atomic orbitals. Here, the orbitals which are belonging to the 4s, then 4p, 4d, and 4f subshells, they will be having different energies. But in the single electron system, they will be having same energies. There in the single electron system, all the subshells will be having same energies. But here in the multi-electron system, we have to consider that the 4s, 4p, 4d, 4f orbitals of different sub orbitals of the subshell will be having different energies, but the orbitals which are present in the same subshell. For example, there are three orbitals px, py, and pz orbital in 4p orbital. See here in the diagram, there will be three orbitals in the 4p subshell, that is 4px, 4py, and 4pz. All these three orbitals will be having same energies, but the subshells will be having different energies. They will be having different energies, but the orbitals in the subshells will be having same energies. A few more features are as follows. Before this, see the diagram. The 1s subshell is at the lower energy level. 2s is having more energy than this 1s subshell. Then 2p will be having more energy. Then 3s, 3p, 4s, 3d. Then 4p, 4s, 4d, 5p, 6s, and 4f. This order of the energies you have studied in the rules, that is rules for filling the atomic orbitals. Here here the subshells will be having different energies. For example, if I consider 2s and 2p subshells, they will be having different energies, but all the three orbitals in the 2p subshell will be having similar energy. In the same way, 3s and 3p subshell will be having different energies, but all the three orbitals in the 3p subshell will be having same energy. The 3s, 3p, and 3d subshell will be having different energies, but the three orbitals in the p subshell will be having same energies, and five orbitals in the d subshell will be having the same energies. In the similar way, 4s, 4p, 4d, and 4f subshells will be having different energies, but the three orbitals in the 4p will have the same energy, and 5 orbitals in the 4d will be having same energy, and 7 orbitals in the 4f will be having same energy. So a few more features which are related to this energy level diagram are given below here. See the points. The first point we have to see is, for the same value of n, higher the value of L, more is the energy of the orbital. That is, if the principal quantum number, the value of the principal quantum number n has same value, the higher and the value of L will be higher, then it will be having a more energy. The orbital will be having more energy when the value is same. Principal quantum number value is same, n is same, and the L value will be high. In that case, the orbital energy will be more. For example, the order of energies of 3s, 3p and 3d orbitals is the energy of 3s subshell is less than energy of 3p subshell and is less than the energy of 3d subshell. If we consider these three orbitals, that is 3s, 3p and 3d orbitals, 3s orbital energy is less than 3p is less than 3d. The second point is the energy difference between s and p orbitals of particular energy shell is small. Between p and d orbitals, it is more while the difference of energy is maximum between d and f orbitals. The energy difference between the s and p orbitals is small and is also small between the p and d orbitals. When we compare the energy difference between the s and p orbitals, then it is small and also it is small between the p and d orbitals, but it is more between the d and f orbitals. That is the energy difference of energy is maximum between the d and f orbitals. Third point is some orbitals belonging to the lower energy shell are present at higher position. For example, the position of 3d orbital is higher than the 4s orbital. See the energy level diagram. The lower energy shell, here we are taking example of 3d orbital, is higher than the 4s orbital. In position, the 3d orbital is higher when compared to the 4s orbital. When compared to the 4s orbital. Lower energy shell. 3d orbital is having lower energy. In the earlier principles or rules, we have studied the energy order. The 3d orbital is having lesser energy and it is at the higher position. 3d orbital is at the higher position than the 4s orbital. The orbital which is having lesser energy is at the higher position and the orbital which is at having higher energy at the lower position. Fourth point is the increasing order of the energies dif- of different orbitals based on the diagram is. Considering the energy level diagram, if we write the increasing order of energies of different orbitals, the order would be 1s orbital, that is energy of 1s subshell is less than 2s subshell, less than 2p, less than 3s, which is less than 3p subshell, which is less than 4s, less than 3d, less than 4p, less than 5s, less than 4d, less than 5p. Then the energy of 5p subshell is less than 6s, energy of 6s subshell is less than 4f, is less than 5d, is less than 6p, which is less than the 7s subshell, and so on. We have to remember this order of that is increasing order of energies of the orbitals. You have to remember this increasing order of energy of the orbitals, which will be useful for writing the electronic configuration as well as filling up of the atomic orbitals. Once again I will repeat, that is 1s energy of 1s subshell is less than 2s less than 2p, which is less than 3h, which is less than 3p, which is less than 4s, less than 3d, less than 4p, which is less than 5s, which is less than energy of a 4d subshell, which is less than the energy of a 5p subshell, and the energy of 5p subshell is less than 6s subshell, which is less than 4s subshell, which is less than 5d subshell, is less than 6p, is less than 7s subshell, and so on. The relative order of the energies of the various orbitals can be predicted with the help of n plus L rule, which is also known as Bohr's-Bury's rule. Here, the order of the energies of the orbitals We are predicting with the help of a rule which is called as n plus 1 rule or Bohrs-Burry's rule. It is called as a Bohrs-Burry's rule, where we are using a formula n plus 1. It is also called as a n plus 1 rule. Using this n plus 1 rule, we can predict the relative order of the energies of various orbitals. So for example, see here, the orbital having the lower value of n plus L will be having the lower energy. If the orbital has a lower n plus L value, it will be having a lower energy. For example, for 4s orbital, we know that principal quantum number n will be equal to 4 and the azimuthal quantum number L will be equal to 0. So substitute the value of n and L in n plus 1 rule. N will be 4 and L will be 0. So 4 plus 0 will be equal to 4. We are getting the value, that is n plus L is equal to 4. For 3D orbital, we know that for 3D orbital, the principal quantum number n value will be 3 and the azimuthal quantum number L value will be 2. So 3 plus 2 will be equal to 5. For 4s orbital, we got the value, that is n plus 1, n plus L is equal to 4, and for 3D orbital, we got n plus L is equal to 5. So since 4s orbital has lower n plus L value, it has a lower energy than 3D orbital. See here in the energy level diagram, we have showed that 3D orbital at the higher position, but we are saying it is having a lesser energy. It has a low energy. The reason for this is you can see here n plus L rule. According to n plus L rule, the 3D orbital has lower energy. It has a lower energy. The 4s orbital has a lower n plus L value. It has a lower energy than the 3D orbital. It will be having a lower energy, so it is placed at the lower level, whereas the 3D orbital is placed at the higher level when compared to the 4s orbital. Why? Because the n plus L value for the 4s orbital is less when compared to the 3D orbital. So the 4s orbital is having a lower energy and it is placed at the lower level than the 3D orbital. Second example is if two orbitals have same n plus L value. In the first condition, we have taken two different n plus L values. Two different n plus L values. But here if we consider two orbitals with the same n plus L value, then the orbital with the lower value of n has the lower energy. In the first condition, the orbital which is having lower value of n plus L will have the lower energy. In the first condition, remember that in the first condition what we are doing, we are considering the orbital which is having lower value of n plus L will be having lower energy. In the second condition, if the two orbitals have same n plus L value, in that case the orbital which is having lower n value, that is lower principal quantum number, that orbital will be having lower energy. For example, for 4f orbital, we know that principal quantum number n is equal to 4 and azimuthal quantum number, that is L, will be 3. So 4 plus 3 will be equal to 7. So for 4f orbital, the n plus L value will be 7. And for 5d orbital, the n plus L value, we know that n for 5d orbital n will be 5 and L will be 2. So 5 plus 2 will be 7. So for both the orbitals, that is 4f and 5d orbitals, we got the n plus L value as 7. We have same n plus L value, which is 7. Here the 4f orbital is having n value as 4 and 5d orbital is having n value as 5. See here, the n value for 4f orbital is 4 and the n value for 5d orbital is 5. So which orbital is having lower value of n, that is lower value of principal quantum number is, that is 4f orbital. 4f orbital is having lower value of n. So this 4f orbital will be having lower energy. We conclude that since the 4f orbital has lower value of n, it has the lower energy than the 5d orbital. Why the 4f orbital has a lower energy? Because it is having a lower value of the principal quantum number n. So it has a lower energy than the 5d orbital. So this was all about today's class. Here we have discussed about the stability of completely filled and half filled atomic orbitals and the concept of exchange energy, and later we have discussed about the relative energies of the atomic orbitals using the energy level diagrams of the single electron species and the multi-electron species. So here I will be wind upping the class. Thank you.